Okay, so we'll do the chapter 6 in this hour, the second half. So basically, we'll talk about some openness of the lens property and expansion and shrinking. Um, so 6.1, we talk about the openness, and 6.2, we discuss some limit sets of the lens, and then we also so in the core section 6.3 we will prove the strong irreducibility of these our orbifolds. So we have this infinite index condition if the fundamental group has infinite index. Okay, so that'll be I, and then the non-pair condition NA if the so intersection of any distinct Pn, the fundamental group only intersects in the finite set. Okay, so that's the so that's related to having. So in the three manifold case, it's related to having some no essential annuli, these kind of things, or so NA implies that every element normalizing K for infinite order K. Uh, every element G normalizing K for infinite order K and infinite fundamental group E of E. That's because if you have uh, any element will conjugate this to some other end, and then if they intersect, then these intersection has to have a finite order. Okay, so that's follows from this condition. Okay, or it has to be inside the group anyway. So uh, right. So SPC is a stable properly convex manifold with a stable and irreducible polynomial group. Okay, and so in definition 6.3, 6.03, so if you have a SPC structure, and then if you look at the some collection of n neighborhoods, and then you take the inverse image, if every straight arc or non-C one point in the boundary of a tilde is contained in the closure of these, then O is said to be strictly convex with respect to the collection of the n. So then O is has to said to have SP structure with respect to the strictly convex. So this is another check error, sorry, but has said to have a strictly convex projective structure. Okay. Now there was some smaller s here, but this is button here. But I mean, you have to have a strictly here, strictly. And so this definition does depend on the choice of u. So but so I mean, of course, but for the if you have a generalized lens shaped or a spherical, and then this definition doesn't depend on the choice of u. Okay, so so it does depend on you, but I think that from here it will be so if you have these cases, it will be independent of the choice of you. So at the moment, this is dependent on you because of the right. Actually, the with respect to collection of n neighborhood here. So, but you can actually make it into n here. Okay, so theorem 6.04 is that so it satisfied IE and NA case, and then only whole spherical lens shape, and then actually this holonomy group is strongly irreducible, and it's not contained in any parabolic subgroup. Okay, so it's stable. So that's what we'll prove in 6.3. So first we show the openness here. So you look at the n fundamental group of the n, and you have this acting on some general length cone neighborhood and satisfy the uniform middle eigenvalue condition, because I mean general length shaped cone is always in the lens shaped cone. So so we have this fundamental representation space. E means that it will fix a vertex here, or the totally geodesic plane, or it's a horospherical. And so so for the generalizations R, and so I haven't really filled in this definition, but there is a definition here in section 3, chapter 3 or so, and these so generalization shaped is a representation acting on the generalization cone. So so the thing is that the so theorem 6.11 is that it always a strongly tame convex projective orbifold, and assume that it is subset. Then E tilde is a properly convex RPN of the O tilde. Then it is generalization shape. It is a strictly generalization shaped. Anyway, so forget about this, because I think that this I will always define. I will prove this much earlier, so I don't think I need this. Okay, so here, so I will drop this later. But the point is that this space is actually the space of generalization representation is open in here. Okay, so um so it is if O is properly convex and satisfy the triangle condition, or E tilde is virtually factorizable, then you can just replace the general lens shape with lens shape in these cases. Okay, so the basically the proof is that the so one I'm not going to do, so but for two, so this will be done in chapter 3 or something later, actually, because we don't need all this theory anyway. So for two, so we know that these satisfy the uniform eigenvalue condition, and so you have these strictly so if you look at the lens K, and then this K mod, this is a compact orbifold with boundary, which is a union of two closed so this is n-1 dimensional orbifold, sorry, like this, and then if it's sufficiently close to original one, so this is smooth, so it is actually C2 convex. So whenever you change the connection, the C2 convexity will be preserved on the change here. So I mean because the C2 so C2 means that the second derivative varies continuously. So if it's positive definite, it's matrix, then it'll still be positive definite after a small change. Okay. So so if it's sufficiently close, then this property is satisfied. So it will be strictly still strictly convex. So you have this lens cone which is strictly convex. So if you have a lens cone, then it is actually strictly lens cone. So strict lens cone. So you prove the lens property is preserved. Okay. And so we can also do this for Tn. So if you have a lens shape Tn, then the space is also this is also stable, and the proof is so you have to convert to the Rn by duality, and then you use that theory here. Okay, and then so corollary 6.1.3. So you have a space of representation satisfying uniform middle eigenvalue condition is still open again, because this is equivalent to lens conditions. Okay, so in 6.2, we define the limit set to be of RPN to be just BD minus partial D for the generalized lens. And this is actually the same definition as the what we did for 5 point in section previous chapter. Okay. And so for Tn, we do the you look at the totally geodesic boundary, and then you remove the from the closure you remove itself. Okay, so then because this is an open subset of the hyperplane, and the limit set of hollow spherical end is only the vertex here. So corollary 6.2.2 is that so if you have a lens shaped or generalized lens or shaped or hollow spherical IPN, then so for any PN neighborhood, CLU BDO is actually just CLS tilde E or this set we defined earlier. Okay, so it is actually independent of the choice of U. Okay, so that's what we are doing. And so, okay. So that is because I mean these are inside the o bar, and then the whatever U is really independent. So these are actually independent of U. So whatever you choose, these will be independent. Okay, so that's why this works. Okay. And so an SPC structure or stable properly convex structure on is a convex real projective structure that orbits a stable irreducible polynomial group and so on. Okay, so so if you have an SPC structure, and then you have U is some collection of disjoint n neighborhood, then the um, every non-C1 point or the straight arc is contained in the closure of a component of some choice of U, then O tilde is said to be strictly convex. So it will have to be strictly SVC structure with respect to collection of ends. So so it is repeated, but I guess so for this our sub case here for this, so we have this restriction on the end. Okay. So so this is actually independent of the choice of U. Okay. Because the set which intersect is invariant. Okay. Okay. Right. And then corollary 6.2.5 is that if you choose a disjoint collection of n neighborhood, then you denote the n, then it's universal cover is in the closure of uh, component for any choice of U. So this just means the independence with respect to U. So next, 6.2.1, we define the convex hull of n. So these are just you want to take some convex hull of this for RPN, this set, and so actually we can show it. This is really the intersection of any PN neighborhood. I mean, taking the convex hull of any PN neighborhood, and you take the intersection of all that. So that's really the same kind of set. Um, right. Right. And this BDI is going to be union of these SVE and this another set. So this will be in the radial direction of this another part of the boundary, and so also these are actually you can define it in terms of concave and neighborhood. So for any concave neighborhood, you take the convex R, it will be the same as IE and so on. Okay, and this for any maximal segment, it will meet only once, and this is actually homeomorphic to this for good cover. So I am saying that because so orbifold homeomorphism isn't really well defined object, I mean concept. So um, well, it is actually right. So but I guess it's kind of not so well defined. Uh, okay, so that's a really all very technical stuff, and the thing we want to define is next we want to discuss about how we expand the lens neighborhood and the horospherical neighborhood. So if you have a horospherical or lens neighborhood, then you can find a set of sequence of lens cone or lens P and neighborhood satisfying this property. And so for any compact subset of the tilde, you can find some integers so that this will contain it. And these are all convex. And the Hausdorff distance can be made as small as possible with respect to this. And so if you remove some UIUJ, then this is just a product of open neighborhood times the orbifold. And so we can choose this BI so that this is smoothly embedded and strictly convex with respect to these. And then the boundary is always in the lambda of this E, the limit set. Okay. So the basic proof is that so you look at these directions. So you choose some finitely many set of segments, and then you take the convex hull of that, and then call it the U, and then so this has a very nice property, and if you take enough of them, you can so this can contain any compact set. And the point is that these are really a proper subset of this tilde because it doesn't meet the boundary of O, and then you can do similar thing for horospherical neighborhood, and also right, and then these you can also smooth these using the smoothing argument that we had, and then we can obtain this these things. Okay, and of course, you can do this for Tn as well. So if you have lens enabled, then you can do the same thing. So the way to do it is to dualize and then take the dual, and you obtain the Rn. And the argument is very similar, but now you have to find something that contains these this set by taking some containing the O tilde star by taking finitely many intersection of the hyperplanes, and you take the intersection under these group element action, and so that you can actually approximate this CL star by these intersection. Okay. So we can take, because we can take more and more hypersurfaces, we can actually do that. Okay. So now we have these things. So now these are actually containing one. So if you dualize, then you have these things increasing and then containing no tilde. But so these are because these approximate it like this, you can also see that this will approximate in the Hausdorff sense using the some previous work in the 1.5.2 and then these will be containing any compact subset or tilde. Okay. So again, this follows from duality. So as long as this happens, then you can see that the Hausdorff distance is goes to 0 here. Okay. And then next, I want to talk about shrinking the lens in the horospherical neighborhood. So for example, if you have a horospherical RPN, then any P neighborhood will contain a smaller horospherical PN neighborhood inside. And then if you have any generalized lens or lens-shaped RPN, it's a convex hull. And then P is any PN neighborhood so that this boundary intersect O tilde is compact. Then if this contains this IE intersect O tilde, then P contains some lens cone. Okay. So this is because this is sort of the minimal of the lens cone. Okay. And um, and also every PN neighborhood will contain some concave PN neighborhood. Okay. So that's shrinking. And then if you have any lens TN neighborhood, um, then any P neighborhood will contain PN neighborhood will contain the lens neighborhood with the strictly convex boundary. And so also you can always choose some mutually disjoint set of lens shape and neighborhood and concave end neighborhood and horospherical end neighborhood. Okay. So for one, you need to use this sphere, so you can always get a smaller and smaller orbifold, I mean ellipsoid where it acts on, because this is the parabolic cusp group of SO and one up to conjugacy, and then you can always do that. And then so for two, you just need to worry about this kind of thing, and then. For three, I guess this means that so the lens can become much as big as you want, and then this will contain anything that contained in the lens cone in the lens in the neighborhood. So and then finally. And so for four, you have to kind of dualize the argument to get the this thing. So if you dualize, this means that you need to find something bigger. Okay, so which contains large sets. Okay, and then I want to talk about maximal concave and neighborhood. So this is the concave neighborhood that is the biggest possible, and because so this is just from the concave and I mean lens cone neighborhood, you remove the convex hull of the limit set, and then you take the one of the component. Okay, so let's see. I mean the component containing the n side and the and so on. Okay, so so in this query, I just showed that this n neighborhood, Pn neighborhood will cover n neighborhood with compact boundary and so on. Okay. So and then this epsilon MC neighborhood is proper Pn neighborhood. So that's because um this concave n neighborhood will embed and then it doesn't it has a good invariance property. So if you take the maximal one, it's still will satisfy these kind of properties. So I prove some invariance property here. Okay. So final 6.3 is a strong irreducibility. So we have this orbifold situation and n neighborhood, and so we have our PN neighborhood we replace with concave PN neighborhood. So here actually I have to have our actual lens neighborhood. I cannot have just generalized lens neighborhood. I need that. So then so in those cases either they if you have any two then they are either empty intersection or they are equal. But they are actually closer and the boundary is empty, or actually they have to be the same. So this property is stronger. You replace with the stronger property at the boundary as well. Okay, sure. So that's the point here. So at the boundary, they don't even intersect. I mean, their limit, the closure doesn't intersect in the boundary unless they are equal. Okay, so the basic proof of that is that so you just need to worry about if you have some points like this, and the point is that because there is a lens, we know that there's a supporting hyperplane, and then every these hypersurfaces are tangent to the radial lines at the boundary, so they cannot actually intersect transversely because then there will be some supporting hyperplane that intersect transversely. So that's the basic argument here, and uh, and then uh, and then of course I have to do this for so that's for RPN, and then I have to do it for the RN and then TPN, and then here again you need to worry about the hypersurfaces that intersect not transversely, but RPN cannot have those kind of things at the boundary, and so on. Okay, so that's the argument, and then finally I show that the so in the virtually factorizable case, there is always totally geodesic P x1, and then D intersect P intersect always a properly convex domain, and D is in here, and this is a compact orbifold. So this is just a repeat of what I said before, and right. So the irreducibility proof is that the so if it's virtually suppose it's virtually reducible, so we take the finite cover so that it is actually reducible, and so then this so let's look at the this surface S where it acts proper subspace where this x1, and then if you suppose it meets this, then this any ended fundamental group will also act on here because it acts on here and then it acts on O tilde. So then this is actually closed before. So this should be so the quotient should be some cross over for homotopy equivalent to this because this is a compact orbifold. So it must be so this N orbifold has a codimension 1, so S must be codimension 1. And so then and of course it will for any other PN it will also acts on there. Okay, so it has the same actually. So these n fundamental groups are all same up to finite index. So this contradicts NA. So therefore cannot happen. So the thing is, if you have any S, then it will only intersect at the boundary. Okay, so uh, so first we show that K is not empty. Because if S is actually empty, then there's an easy argument to show this cannot happen. And if not, then this is some kind of open convex domain, or it's just a cone like this with some PN neighborhood. And because of these because this also is in the n fundamental group, where the n fundamental x go compactly, and so so then these are actually invariant under the whole group. So this TJ is okay. Okay. So that's just a very technical thing then because we just need to work through the um uh, so some things here right. So this A is showing that K is not empty. Okay, so those parts are just very simple arguments. Okay. And then for part B, where I am showing this, so we only have to worry about RPN by taking the dual, and then so if there's something which sends this vertex to non-vertex, and this is in K, then so then you have to work with the concave band neighborhood, and then you either have to follow from there. And so again, using this concave band neighborhood, you show that they're empty or they're the same. And then you use this because these are reducible, partially factorizable case, you just need to work with this center argument, and then these. So K has to be one of these, but these are not properly convex, so only this case exists, and so on. So we find some contradiction using this. So the final part is 6.6.3. So if you have a strict SPC orbifold, then it will satisfy the triangle property, and every generalized lens are actually lens. Okay. So the generalized lens can be promoted to lens. Because if not, then so you have this kind of lens neighborhood, and this you have some concave band neighborhood, and if you have any triangle, so triangle is straight, so have three straight lines. So so these all have to be in some RPN neighborhood, at least the two of them. But each edge has to be in one of them, okay? One of the PN neighborhood. But this corollary wants 6.31, so that says that if you have any closure meets, then they have to be the same. So they are all in one of them, okay? So if you have everything is in one of them, then then this means that triangle is always edges are all inside here. So that means that triangle condition is satisfied. So therefore it is lens. So if you have a triangle condition satisfied, then it's lens. Okay. Okay, so that ends today's lecture, and we'll continue chapter 7 next time.